All right, guys, I'm sorry I sound absolutely awful, but here is your video for today. I might have to do this in two parts, so I'm just going to warn you now. What we are going to be able to do by the end of today is you're going to be able to use electronegativity values to determine polarity of a bond, and you're going to be able to name and write the formula for covalent molecules, all right? So it's kind of a two-parter today, right? Yesterday, we learned that covalent bonds are bonds formed between the sharing of electrons, and it's two or more nonmetal atoms, all right? And we did Lewis dot structures yesterday to show us how we can write covalent bonds and show the sharing of electrons through single, double, or triple bonds. Okay. However, we have two types of covalent bonds that exist. One is called a nonpolar covalent bond, and one's a polar covalent. And nonpolar covalents are covalent bonds in which electrons are equally shared, okay? So when I'm sharing those electrons, right, they're equally shared between the two. So for example, if I have H2, right, or hydrogen, the electrons, the two electrons being shared between the two hydrogens are being shared equally. So each of them are getting equal amount of time with their electrons. Polar covalent, however, is electrons are shared unequally. So one element in the bond is a little bit more selfish and wants to hoard the electron closer to them. So they're still sharing, but it's a little bit more of a one-sided situation, all right? So when we talk about polar and nonpolar, we're talking about the polarity of a molecule, okay? Polarity is the tendency of a molecule or a compound to be attracted or repelled by electrical charges, meaning I'm either going to attract or repel negative or positive charges, because there's an asymmetrical arrangement of atoms, right? Meaning that what's on one side of your molecule is not the same as what's on the other side, okay? So essentially, it's when a molecule acts like a magnet, and we started looking at that with ionic bonds. Sorry, guys, I'm eating breakfast right now at the same time. Okay. So, one side of the molecule is going to want more electrons, and so it's going to be more negative, and then it's going to act more like a magnet, okay, wanting to attract a more positive, right? And this is always based on the electronegativity of an atom, and we started looking at electronegativity last unit when we talked about trends. So we're now going to use that to be able to determine polarity, okay? So this is my electronegativity table, okay? It gives electronegativity values for each element, right? So you see for fluorine here, it's the highest electronegativity, and we know that because we said that fluorine was the most electronegative, right? We don't talk about our noble gases because they don't want electrons, right? But fluorine is my most electronegative at 4.0. My least are down here, right? So that follows our trend of increasing electronegativity as I go across, decreasing as I go down. All right, so we're going to be using these values, this is in your notes, okay, to support our answers for polar and nonpolar, okay? So when I am determining polarity, okay, what I do is I'm going to find the difference between the electronegativity values of my two atoms that I'm looking at, all right? If I have an electronegativity difference that's 0.4 or smaller, I'm going to have a nonpolar covalent bond, okay? If it's larger than 0.4, but usually less than like 1.7, most of the time I'm going to have a polar covalent, and anything really higher than that, if I'm getting into the 2 range, I'm going to have ionic. There are exceptions though, right? Sometimes I'm going to have a value that's going to be closer to the polar covalent, but I'm made up of a metal and a nonmetal, okay? At the end of the day, when I'm determining polarity, the essential composition of my atoms matter first. So if I have a metal and a nonmetal, I'm always ionic, okay? If I'm just nonmetals, I'm covalent. And once I determine it's covalent, then I can determine nonpolar and polar, okay? So let's look at this here, right? we have nonpolar covalent bonds. They are equally sharing electrons, all right? Sorry about that, right? And I have an electronegativity difference of 0 to 0.4, right? So let's look at this example here with F2, right? If I have two fluorines and I'm looking at the bond between fluorines, right? This element here has an electronegativity of 4. This element here has electronegativity of 4. So when I subtract the 2, right, my difference between the two, I have a difference of 0. So that's going to fall under nonpolar covalent, okay? Let's look at CH4, right? When I draw my Lewis dot structure out, I get this. And if I want to look at that bond between my carbon and one of my hydrogens, right? Carbon, when I look on my chart, right, has an electronegativity of 2.5. Hydrogen has a 2.1, and so I have an electronegativity difference of 0.4, right? And that falls in the nonpolar covalent region, right? So these are two examples of nonpolar covalent bonds between atoms, okay? Polar covalent is the unequal sharing, okay? And when I have an unequal sharing, I have to have a dipole that is shown, and that shows that it's an uneven distribution, okay? Meaning one is going to hoard more electrons, right? And so this is represented by an arrow, okay, pointing to the more electronegative element or atom, okay? And these electronegativity differences is between 0.4 and 1.9, right? So if I have H2O here, right, the bond between oxygen and hydrogen, right, oxygen has electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So my difference between the two is 1.4, right? When I subtract them out, it's 1.4. So that falls in my polar covalent bond region, right? And what's that saying is oxygen, because it's more electronegative, wants to hoard more electrons, right? And so I would have a dipole moment. Let me put this in here, right? I would have a dipole moment. Wow, this is going to frustrate me. That's going to point towards my oxygen because oxygen is more electronegative, okay? Hydrogen and fluorine, when they're put together, right, and I find the electronegativity difference, fluorine has a 4, hydrogen has a 2.1, so I have an electronegativity difference of a 1.9, right? I'm going to be in that polar covalent region because I'm a metal and a non-metal, okay? And so because I have that polar covalent, I have to put my dipole moment in, meaning that hydrogen, right, is going to be more willing to give up that electron, right? And fluorine wants to hoard it, right? So my dipole moment is shown here. And in your notes, you guys have a graphical, like, representation or an actual, like, representation of this, HF, right? Showing that F has a lot more electrons and is bigger than my H in my bond because of that unequal distribution, all right? So what I want you guys to do right now is I want you to use your chart, right, of electronegativities, your periodic table that shows the electronegativity values, and I want you to look at each of these and I want you to determine if they're ionic or covalent, and if they're covalent, if they're polar or non-polar, all right? I'm going to stop the video here and I'm going to put a part 2 up, okay? So do this in your notes and then come back to part 2.